he has another
Good morning,
guy
all.
also looking at from another brand too, and they're not.
A few
They're in the
housekeeping
same
items here.
situation that you're in. You're like,
About 45 minutes, and then we'll have question and answer session afterwards that we're hoping everybody participates in. So, yeah. So without further ado, it's my pleasure to introduce Gene Mason here. He's been an engineer for a very long time. His words, not mine. I'd say he's very experienced. He has more than 40 years of experience in the ocean engineering. He got his start in the Navy, doing a lot of work with the Navy, including a lot of projects. That's very, very interesting. We talked about engineering today. And now, for the last 29 years, he's been working for MBARI, where he has worked on and deployed in the ocean a very wide variety of ocean observing systems. And his current focus is in this BioGeo Argo in Ken Johnson's lab. So, yeah, please welcome Gene.
Good morning. Thanks for the opportunity. I'm looking forward to this. So I'll talk about some work we've been doing on a profiling float optimized for coastal applications, the work we've been doing at MBARI. I'll talk about some science opportunities and tech transfer possibilities. So start with an executive summary and then fill in the details later. We're finishing the development of a coastal profiling float system targeted at better understanding the health of the ocean. That's how Ken describes our lab's work in a very few words. The CPF is optimized for use from the seabed, can actually park on the seafloor, to the surface of the coastal zones and upper 350 meters of the world's oceans. My science colleagues tell me that's where the bugs are, so that's where we're working. We unfortunately called the coastal profiling float. That was the initial target, but it can be used anywhere in the ocean as long as you don't go deeper than 350 meters. We support the full GoBGC suite of biogeochemical sensors, CGD, everything that goes in the ocean seems to have CGD on it, oxygen, pH, nitrate, fluorescence, backscatter, optical radiation, and we have supported a range of other instruments also. I'll talk about a few of those. We're discussing ways to move the CPF technology out to the greater community. MBARI has an explicit goal of moving the technology we develop out to the community. This seminar is one of the opportunities to engage the community and need to find out how we might be able to do that. So that's the summary. Hope you stick around for the details. The initial motivation for this project came, I had been working with Ken Johnson before I worked in his lab as an engineer. And we had some great projects together, and I asked him what was next on his list. And he showed me this NOAA news bulletin published in 2008, Unfavorable Ocean Conditions, the Likely Cause of Low Salmon Returns Along the West Coast in 2007. When you read the details, the data came from 2005. So the take-home message, the point Ken was, I think, trying to make is that everyone needs more data. We need more data, we need better data, we need it faster. I don't think that's controversial. I think probably everyone in this room agrees that we don't get nearly enough observations in the ocean to do the work we'd like to do. So a more current motivation is NOAA Future Seas. A lot of what I'm going to talk about, this group probably knows a lot more about than I do. I apologize. I hope I get it right. Please correct me where I get it wrong, but NOAA Future Seas is, to my eye, a very ambitious model-based approach to evaluate the impacts of climate change on U.S. managed marine species and identify climate-resilient management strategies. So if you look at this picture right off their webpage, it starts with a couple of models, the global climate model and the ROMS model. I worked in a modeling group in graduate school. I worked with Yi Chow, who was one of the developers of ROMS, which is, I think, this ROMS model here. Every modeler would love to have data to help calibrate and validate the model. There's a possibility we may be able to provide some of that data. So more motivation. I worked in the Arctic, as Noah mentioned, for 4 springs. It was a very challenging and satisfying experience. When I looked at NSF's 10 big ideas, one of them is navigating the new Arctic. So the picture on the left is salmon, at least to my eye. Polar bears never had to share their ecosystem with cruise ships. Now they're an advertisement. This is right off an advertisement for the Stellar Travel Company, where they're using polar bears as a way to market cruise ships in the Arctic, which is unfortunate. Good news is NSF at least realizes this, and one of their 10 big ideas is navigating the new Arctic with the same conclusion: not enough observations, sparse and inadequate in their words. So there's a lot more applications. I'm not going to go into them in great detail. Again, you know more about this than I do. Harmful algal blooms, oxygen dead zones, marine heat waves, all these things are targets that might be suitable for a CPF-based observing system. So there's another application that's more recent, at least to my experience. I have a couple of colleagues, friends actually, in the marine CDR, marine carbon dioxide removal business. One on the science side, one actually is the VP of engineering for a company that's running a pilot project right now. My friend came to me and said, "You make measurements in the ocean. We need to make measurements in the ocean. What can I learn from you?" So it's a great conversation. I started with my usual question: what are you trying to do? In the hopes of answering some of these more detailed questions. What variables do you want to measure? What spatial scale? What temporal scale? What data products are required? And probably most important, what's your budget? And I had those are the generic questions I ask kind of anybody who's interested in starting an observing project in the ocean. There were some more. I've done a little bit of homework on this task before we met. And there seems to be two sides to the MRV problem for MCDR. One is companies that are selling systems need to know how much, need to be able to say how much carbon they removed from the ocean in order to get paid back by the gigaton or whatever unit they're working in. So that's important. My concern is on the other side, and it isn't clear to me whether it's equally more or less important to know what the effect of these marine CDR systems are having on the ecosystem. And when I did a little bit of reading, the vast majority of reading that I saw had to do with people addressing this problem from a modeling perspective. So one of the questions I have, I worked at a modeling group in graduate school, we needed data. Most of the models that I'm familiar with need data. So my question is modeling all that's required now or in the future. So not surprisingly, my conversation with my pal, the answer to all these was the basic, I don't know. So that's fine. That's not disappointing to me. I actually love challenges where there aren't very many answers. It'd be nice to have one or two. But it appears, if I understand this field correctly, that there's still a lot of work that needs to be done to refine what an MRV system for marine CDR might look like. So in the course of educating myself, I came across this chart that I'm hoping you can see. If not, I'll explain it in Science News. I actually think this chart came from a NOAA paper on NOAA's approach to marine CDR, and it might be that some of the people who actually created this chart are here in this room, in which case I apologize for whatever I missed. But basically, there are a variety of marine CDR applications here. The size of the blue dot has to do with the storage duration in years. The bigger the dot, the longer you'll be able to sequester carbon using this approach. The x-axis is the cost in dollars per ton of CO2 removed. The y-axis is the possibility of how many tons of CO2 can be removed per year. So if you pick either one of these, direct ocean capture or enhanced rock weathering, let's just take this one, enhanced rock weathering, $60 per ton of CO2 removed. Is there somebody asking a question? Did I hear something?
I think it's just noise, Jane.
Right. So $60 a ton and roughly 7 billion tons. Well, I multiplied 60 tons times 7 billion tons. That's $500 billion if I got the math right. And I kind of think that for 1/10 of 1% of $500 billion, we can probably do a pretty good job at building an MRV system for MCDR. Just yes, but I'm thinking we're in the ballpark from a budget perspective. Now, that's a gross overinflation of the money that's available. I recognize that. A couple orders of magnitude, we'd still be well funded. So that's a possible application. Okay, so that's the background. I'm going to talk a little more about details now. I'm working the chemical sensors group. That's a picture of us working on the MRA's workboat, the Paragon. That's Ken Johnson, my boss, right there. That's my friend and colleague, Peter Walls. We're deploying an Argo float in Monterey Bay This is the Paragon. That's one of its two 350 horsepower engines. And what you can't see in this picture is me driving the boat. So it is one of my favorite things to do is work at sea. And the fact that they let me drive, and already lets me drive a 700 horsepower workboat is kind of amazing to me, but I much enjoy it. So right off our website, the Chemical Sensors website, we develop sensor flow technologies to record fundamental ocean properties. Our research target is, as I mentioned before, understanding the health of the ocean. We've developed pH and nitrate sensors in our lab, and we've commercialized both of those. We're heavily involved in the SOCOM and GoBGC projects, which are both pretty big projects. SOCOM was $20 million and put, if I remember right, 200 BGC floats in the Southern Ocean. GoBGC is more ambitious. It's a $50 million project aimed at putting, if I remember correctly, 500 floats globally, 500 BGC floats globally. So big projects, and we're doing a lot of the work in our lab. So why does our lab focus on profiling floats? And these are actually my words, I believe these. Might be a bit cultish, but it's arguably profiling floats are the most cost-effective observing platform for long-term ecosystem scale applications. People's input in our lab, that's just a given. We're a float lab, so not surprising. But some ways to justify that. We're currently paying about $90K per BGC float. You can deploy them almost any boat or ship of opportunity to get to the deployment site. The bigger the boat, the more you can deploy at one time, but you could deploy GoBGC float off a rowboat. If you had someone who could row out to the places you want to go to, you could deploy one. You could deploy two, depending on the size of the rowboat, but it doesn't take a lot of assets. Probably need a boat with a davit to get it back safely, but still, not a big boat. The maintenance costs for a profiling float, near zero. There really isn't much. Keep it over the side, and you really, ideally, don't touch it for 5 to 7 years. At least that's the experience with Argo and GoBGC floats. I say near zero and not zero because there are times where people have had to go out and, for example, position a float, but not very often. So amortized over the number of floats, the number of years, not much cost. There is a fair amount of money, though, that goes into data processing. That's a fact, but it's true for any observing system. And the amount of money you put into data processing is dependent on how much money you have. So it's independent of whether it's a profiling float system or not. You have to pay for data processing. There are several programs in AUVs and ROVs, and we use a lot of language also. So I recognize that floats, while pretty darn cool, they aren't the silver bullet for all applications. So I'm willing to accept the provision that a full-up CPF-based observing system might also have other assets in it. And I'll point out in this picture, which is entirely a cartoon, there are some anchored fixed CPFs, and I'll talk about those in a few minutes. But if you want to put a glider in, want to put an AUV in, there's certainly ways to improve the spot measuring capabilities of a fixed float or the Lagrangian measurements of the floating float or a drifting float. So you want to look at a particular feature, you want to stay with the feature. AUVs, gliders can do that. We're doing that at their part. So there are opportunities for other platforms. So data is important. I'm an engineer. I've done a lot of signal processing over the years, not necessarily a lot of oceanographic data processing. But I learned early on that our lab's deliverable is relevant, defensible data products. So quick side story, James Carville was a political consultant who helped get Bill Clinton elected president. The story goes that he had a sign behind his desk that said, "It's the economy, stupid." Anytime a young, energetic volunteer would come up and say, "What should I be focusing on to help get Clinton elected?" he would point at the sign and say, "It's the economy, stupid." I can tell you for a fact, and I have several various stories to back this up, that I wish we had a sign in our lab that when I started working there said, "Data stupid," because I came in thinking it was that technology, floats and the sensors, but really we're building floats and sensors in order to deliver relevant, defensible data products. Luckily, a big part of our lab is very involved in the Argo BGC data processing and QC pipeline. I am astounded how much work it takes to provide defensible data products in this research area. It's not necessarily a big problem for things like temperature, even oxygen, but there's a tremendous amount of work that goes into providing what I think are close to state-of-the-art pH measurements that we make in our lab. So we'll talk about that a little more as time goes on, but the point here is from day, maybe not one, but it's day 2 or 3, the CPF has been generating files that can feed the GoBGC data pipeline that we've built in our lab for the GoBGC programs. So that means a lot of things. What it means in this particular case is our initial target for feeding data is FloatViz. I don't know how many of you are aware of FloatViz. It's something we've had in our lab for a long time. Ken actually wrote it decades ago. It is a web application that takes float data in the native formats that Argo floats generate. The CPF generates those same files. And you can do some very basic data visualization and download data files. So you can say, for this float number, pick a float, select one X variable, and you can select multiple Y variables, and you can plot the data. You can also download the data. And you can do a little bit of data sorting based on X and Y values, and a couple other things, min-depth, max-depth. It's not a full-blown data management system, but what I understand, what I know is if I can get my files into FloatViz, then they will become available to all the GoBGC data products. So this lower right is right off the GoBGC data page, and you can download data from the GoBGC website from FloatViz, like I showed above, Argo GDAX, GoBGC and SOCOM data archives at UC San Diego, ERDAP, WebODB, and there's a bunch of others. So again, is the data stupid? And so I need to make sure that the data we generate can be available to people outside of our lab. So my goal is FloatViz. Once I do that, pipelines are in place to get the data to more places that are generally more accessible to scientists. So we have done other science along the way. One of the most interesting projects we did was with Magdalena Carranza, who now works in our lab at MBARI. She's interested, she's a physical oceanographer, she's interested in vertical mixing. This was a paper and a poster she presented at a Gordon Research Conference on ocean mixing. Her question was, can we infer vertical mixing rates from Argo float ascent rates? I'm not going to try and explain the science here. I did do some turbulence work in graduate school, but it would just be embarrassing for me to try and explain this. But her idea was that if you could equip a CPF with high quality turbulence sensors, then you would be able to compare that to the BGC data that got acquired and see if you could actually infer vertical mixing rates from the BGC sensors using the turbulence sensor as ground truth. And if you can do that, then you would have a eventually global way to measure vertical mixing rates. So that's exciting. And she published a paper. One of the most interesting things that came out of it is this right here. This is part of the poster that she provided. And a surprising result is the CPF is an ideally client platform for turbulence measurements. Apparently, people who make turbulence measurements need a platform that is not vibrating. It's not acoustically noisy or vibrationally noisy. That affects, contaminates their measurements. And in our case, you can see on this slide on the slide on the right, which is the vibration sensors on the turbulence sensor, there's near zero vibration. Surprising result. We didn't know that was going to happen, but it was very pleasing. It's a microwriter turbulence sensor from Rockland Scientific. We were working with Rockland Scientific very carefully to do this job, and they were ecstatic at the quality of the data we were providing. So good news. Noah mentioned that I worked for a defense contractor before I came to MBARI. We did a lot of acoustic underwater systems, and we had the same problem. And it looks to me like I would love to put a hydrophone or a hydrophone array on a CPF and have whatever, a fixed or a Lagrangian way to make acoustic measurements. There's a variety of applications, as I'm sure you all know. So switch gears for a second. We'll talk about the CPF. First thing, functionality. It's designed to work from 0 to 350 meters. The pressure limit is the pressure hull. The pressure hull was designed for the range where the bugs are, which is the upper 200 meters. So I said, okay, you want 200 meters, we'll give you 350. I designed pressure vessels for a living. Designed pressure vessels up to 6,000 meter pressure vessels. And so I overbuilt this by a little bit. The only limitation to going deeper is the pressure hull at this point. The big limitation we'll talk about in a few slides. It's the sensors. But, okay, so the CPF is a very standard profile. There's only a couple of things I consider to be novel or improvements to the state of the art. One is the buoyancy engine. So we can pump 3.5 liters of buoyancy from the inside to the outside. That means we can get 3.5 liters of positive buoyancy, or say it differently, we can, if we're perfectly neutral when we go in the water, we can get 1 3/4 liters positive, and we can get 1 3/4 liters negative. That's a lot. For example, the Apex floats have, I believe, 270 mils of oil, which is about 1%. Not even enough to break through a freshwater to normal salt water microclimate. Zero PSU to 35 PSU is about 2.5%. We have 9% of our total volume. So that matters because if you have a 1,000-liter platform, having 10 liters of buoyancy control isn't very much. Whereas 40 liters, we have 3.5 liters, that's about 9%. It also means we can go faster, 0 to 47 meters per second. There are applications, at least naval applications, where they need to go fast. And we made no effort to go fast. We can certainly go faster by reducing the drag factors on these things, but we can right now do 0 to about 47 meters per second. The normal ascent rate for Apex floats is about 10 centimeters per second, but we can descend faster and save energy there. So the other thing we did with this 3.5 liters is we did a way to mitigate drift in the coastal zone. If you're in the open ocean, you have a float drifting west, it's not a problem. There's 3,500 other floats to the east, so one will fill in. That is in fact what happens with the Argo floats. The ocean does a remarkably good job of keeping about 3,500, and actually it's closer to 4,000 Apex floats floating around the world's ocean. You're relatively evenly distributed. So that's not true of the coast. We have a float drifting east on the west coast, it winds up onshore. And we don't have a bunch of floats offshore filling in gaps. So we need a way to mitigate drift. And by and large on the west coast for sure, drift is generally onshore and offshore. So one of the ways we do that is by anchoring on the bottom. This 3.5 liters gives us about 1/2 liter, as much as a liter. It's our choice how much we want to anchor on the bottom with. So based on my simulations, that's not nearly enough to keep the CPF from skipping along the bottom in all current conditions. But it is enough to keep the CPF in place for the vast majority of curve profiles that I've looked at near the bottom. So that's good news. It also gives us reserve buoyancy to offset biofouling and mud buildup. You're going to work in the coast. Biofoulic's a problem. You aren't going to solve that problem with the CPF project. There will be stuff growing on the CPF. So we need to have some reserve buoyancy to combat that problem. We're going to anchor on the bottom. It's going to wind up somewhere on your channel. So we need to be able to handle that. And we do. And the other thing it does is a side product. If you're familiar with how Apex floats get ballasted now, any platform in the ocean that has to get ballasted to near neutral, it's remarkably irritating how hard that is to do. And when you have all this spare buoyancy to deal with, to live with, to work with, you don't have to get that close. We basically ballast with lead bars that are 350 grams a piece. So you get to within 350 grams and you're good to go. Spray gliders, these are the gliders that we use, the long-range ADV and Abari, they need to get down to a few grams. It's really an irritating process. And then you have to decide what temperature and salinity range you want to work in. And if you get it wrong, you can't break through the so really irritating. We kind of get through that with brute force. Okay, I talked about sample recovery. This is one of the other science projects that goes on. This is an early prototype of the CPF. You can barely see it, but it's right here. This is one of 2 CPFs that the biological oceanography group at MBARI is using. There's 2 segment traps. Here's one. There's room for another back here. I don't know if you can see it, but there is a mounting bracket there. There's only one mounted here. And there's an acoustic modem. So it'd be nice if I could tell you we designed the Ferrari of the sea. We did not. We basically designed the Ford F-150 pickup of the sea. So we can put stuff on here, and if it's roughly neutral, CPF can handle it. So that's good news. We've done a lot of fairly awesome things. The micro rider that I talked about earlier, those were pretty big sensors. And we didn't really have to do anything with respect to balancing, except pull out some of the extra lead that we installed. Brett Jones, one of my friends and colleagues. Science payload, we have 9 sensor ports. To us, a sensor port is a communication port. We can handle a variety of protocols. Basically, every instrument that I know of is a serial port, RS-232 port, so we have 9 of those. We can also deal with I2C. We don't do Ethernet, it's simply too power hungry. But there are 6 ports that we're using for the BGC suite, and we have room for 3 more, which we had to use on occasion. So we can handle up to 12 sensors. Again, not much different than any floats you've seen before, except for the fact we have this giant internal bladder and external oil bladder. And we're using an industrial hydraulic pump that gives us much better control over pushing and pulling oil in and out. And I'll talk about that in a minute. Iridium communication, we've been doing short burst datagrams with Iridium SPD since day 1, and we're finishing up our Rudix comms right now. So the modem has always been able to do Rudix. We had to finish some of the shore side infrastructure to handle the Rudix communication. SPDs are good for short messages. We'll send those with a small amount of science data and a large amount of engineering data. If you really want to get all the science data off the platform after every profile, then you need this Rudix point. It's still not very fast, but it's better than OMS and SPDs. We have good platform velocity and depth control. I told you we had a kind of a snazzy little industrial hydraulic pump. It pumps in and out, which is not the case for most floats. And so we have closed loop control over platform velocity and depth control. Not sure how much of this you can see. I hope the whole thing, but here's depth or pressure along the vertical axis and time. So we're at the surface. We dive down to 35 meters. We hold depth at 35 meters, plus or minus, we come back to the surface. This right here is a blow up. This right here is a blow up at the top of 10 meters. And you can see we acquire the desired descent velocity within a few 4 meters or so, and we're going the velocity we want. If you're working on the coast, you don't want to spend 50 meters of your 60-meter depth trying to get down to speed or up to speed. You can see in this slide, we have a deadband. We need to save energy. We can't run the control loop at full speed all the time. It takes too much energy. So in this case, we have a 2-meter deadband dialed in, and you can see it oscillates in that 2-meter deadband with about a 0.9 meter standard deviation. Very much what we expected. If you do run the control loop full time, you can get the with no deadband, you can get the depth jitter down to less than 0.14 meters. So that's good. If you had some specific application where you needed to keep depth very precisely, we can provide at least some of that solution. So current and future work, here's what we hope to do this year. Finish the power management, all the technical functionalities there. We just need to finish the software with the goal of getting, our goal from the beginning has been 200 meter profiles spread over 1 year. And the goal here is that when you're sleeping, it takes to near 0 power. So we don't care whether you burn those whole 200 meter profiles in the first 10 days or spread it out over a year, because our sleep energy is near 0 compared to the profiling energy. I mentioned Iridium Rudix, we have to finish that. We have 2 CPFs in addition to the one we've been testing and doing science with. We have 2 more that are basically 90% done that we're going to finish this summer. And then we run more MRI science missions with that FloatViz data pipeline. Here's what I'd like to do. Early on, I mentioned to Ken, I don't think this Lagrangian approach to a coastal profiling float makes a lot of sense. We spend a lot of time worrying about where the float is. And I'm a trained mechanical engineer. I built several winches for a living. Mechanical engineers love to build winches, in case you didn't know. And so I said, couldn't we consider a winched approach? And the answer was no, get out. We're a Lagrangian lab. We're a floating lab. Ken has a set of science he wants to do. Lagrangian does the job. But there are applications where you may want to be fixed in place. So I have a conceptual design. This is not hardware. This is a SolidWorks design for a winched CPF. Gets smaller, gets shorter, because you don't need to store 3.5 liters of oil in the CPF. You don't have to put 3.5 liters of bladder on the outside, but you need to put a winch. So you may or may not believe me, but underneath this skirt, there is at least a conceptual model for a winch with 200 meters, actually more than 200 meters of line on it. The other problem I mentioned earlier is this problem of drift. And the theory is our risk mitigation strategy at the beginning of the project was, okay, we know we're going to drift, but most places in the world, the drift happens when you're on, most of the drift happens when you're on the surface. You're getting pushed either onshore or offshore. If I believe my physical oceanographer friends, that means there has to be some current at depth going the opposite direction. We can find that current, we can park there, and we can drift somewhere opposite to where we're drifting on the surface. So this slide here is a little experiment we did where we just, in March of 2017, a long time ago, we just did our normal 26 profiles. We started here, we ended here, we anchor on the bottom every time. 26 profiles, we wound up traveling about 5 kilometers due west. Then, a couple months later, we got a chance to go back down. And we did an experiment in the same location, close to the same location, where we didn't anchor on the bottom. We didn't know what depth to park at because we can't measure velocity, but we parked at a couple of different depths. And we just used our eye to manage to decide what depth to park at. And instead of this linear east-west track, we got a more circular track. So that's the evidence I have that by parking at appropriate depths, we will be able to navigate the float. So how do you measure current on a Lagrangian device? Kind of hard. If you're floating at the same speed as the particles in the water, then kind of hard. But we have done some initial work on using inertial measurement units. Everyone has a phone with an inertial measurement unit in it. They're not sensitive enough to do the job. But instead of the $50 float, $50 inertial measurement units, it's possible that $2,500 inertial measurement unit can get you an idea of, we don't care about the exact velocity and we don't care about the exact direction. I just am looking for a current that's roughly opposite to the drift, plus or minus 45 degrees, and positive in that direction. So I don't need a number. I just need to know it's positive in the direction I want to find. So that's a possibility. And then tech transfer, I'm very enthusiastic about moving the tech out of the market. So quick status summary. I mentioned most of these things. What I do, 2 early CPF prototypes are used routinely by Barry's model group without my intervention. So that's a key point. And then 1 box CPF is being repurposed for Colleen Durkin's carbon export work. She's developing some kind of imaging system that I'm not too familiar with. I don't know how much technical readiness levels apply to this group, but NOAA has a technical readiness level scale, 1 to 8. 1 is concept, 1 to 9. 9 is the system is deployed and used routinely. So if I had to pick a number, I'd say we're somewhere in the 7-ish category for technical readiness level, which according to the NOAA document, prototype system demonstrated in near real world environment, subsystem components fully integrated in the system. It's true, we've actually demonstrated the system in actual real world environments with real world science, and all the subsystem components are integrated. They aren't working as well as they should. So we need to improve them, but they are working. So we're 7-ish. I call it 6, I'd be okay with that. We want to get to 8, we want to get to 9, and as we all know, there's this tech canyon and trap or river of crocodiles getting from this TRL7 to TRL8. It is really hard. So let's talk about, switch gears to tech transfer. I'm aware of a couple of different ways to get tech collaborations. Happy to talk about it. Commercialization, as I mentioned, we commercialized 2 instruments we developed at Imbari, the pH sensor, the nitrate sensor. There is a possibility that this thing could be open sourced. This is a little bit, it's not a little bit controversial, it's controversial, it's not clear if it can be done. But it's a possibility, and Noah and I have been talking about it. It actually has some huge benefits. I'm going to talk a little more about that. I hope that someone else's opinion besides Noah and mine, because we could be perceived as biased on this. There may be others, I just don't know them, so I'm happy to hear. If you've got them, let me know. And this is that same CPF that I showed you earlier being deployed by the Biological Oceanography Group. Not 100% clear that pink sea boots are a requirement to run the CPF, but you can't argue. They kind of look good. So here's the tech transfer options. Collaborations, CPF system is interested in you. Please, let's talk. I'm here. Commercialization. There's some pros. Pro is anyone can buy a CPF, theoretically. It actually is not true for all technology to be commercialized. There's just not enough pH sensors floating around. If you were to go to Seabird and say, hey, I want CPS, one of the pH sensors on your website, you get a pretty long lead time. So, but for a lot of other sensors, you can go buy a CG, go buy an oxygen object, go buy an OCR. So that's the pro. I admit to being biased. I can't think of any others. You can go buy one. It's an awful lot of cost. They're expensive. It's astounding how the price that's being charged for some of these instruments is unrelated to the cost of parts and manufacturing at a reasonable profit. I do that for a living. I know how much it costs. If I multiply by 2 to get a reasonable profit on there, the price is kind of amazingly high. The other thing that happens is development stagnates. Companies get a product, and I haven't seen much improvement in many of the technologies I keep track of. In fact, since most of these small oceanographic instrumentation companies get bought by much larger global multinational evil empires, they aren't interested in sinking more money into this small market. Reliability suffers tremendously. It's kind of astounding how poor the reliability is for a variety of instruments and platforms that to me are pretty straightforward to build. Almost always when you commercialize something, you have to give the company an exclusive license. That means you have sole source risks. We got hit pretty hard with this on the GoBGC project. When Honeywell decided they were going to stop building the ISPET sensor that is the heart of the pH device. The other thing is you only get a product when you go to a company to buy an instrument or a platform. You don't get all the rest of the system you need to run a successful project. New applications, pretty much done. And even if you're only going to deploy a CPF or whatever, a couple months a year, to buy one. It sits in your lab for years while you're not using it. So open source, what are the pros? Basically the exact opposite of all of these. And I'll talk about this in more detail, but every one of these is pretty much the exact opposite. Here's the con, not a small one. I don't know that it's feasible. So I'd love to get some input on when the risks that I'm going to talk about can be mitigated. So I don't think you have to read very far between the lines to see what my preference is. I'm all for open source. I think we have a great logo for coffee cups and t-shirts, so that's step 1. And if you look at this slide, on the right is this graphic from the NSF solicitation for codes, pathways to enable open source ecosystems. It's kind of an awesome solicitation. It's really well structured with a phase 1 and a phase 2. In that solicitation, we show what NSF thinks are the major components of an open system ecosystem. In my mind, when I read a solicitation, the most critical element for a CPF-based open source ecosystem is an appropriate sized group of users. I don't exactly know what that is, but I'm going to theorize that it's roughly 10 CPFs a year for a couple of years. I'll explain why that number's so low in a couple of slides. If I was you and I'd say that number, saw that number, I'd say, no way are you going to be able to make a living building 10 CPFs a year. Let me explain that in a few slides. If there are 3 to 5 projects using a few CPFs a year for many years, that's also possible. And there is another way to make a closed system work. And if you have one large volume need, everyone else can tag along on that large volume need. And I'm looking at you, MRB, for Marin CPR. There might be 50 pilot projects over the next 10 years globally. And if every one of those needs 5 or 10 CPFs to run their MRB program, we're in there. So that's step 1, but there's a lot of other things that have to happen. Step 2, somebody needs to be the hero, a group or person, but there needs to be one committed, motivated CPF group. Could be a research lab, could be a company, could be a variety of things, and I'll talk about a few later on, but they have to handle all these things. By the way, engineer is not on the pose graphic. I added that because I need engineers involved in the CPF system. So, second most critical, committed, motivated CPF. Next most critical, a source of CPFs. So, it's a long conversation. Certainly, at 10 CPFs a year are not going to excite any for-profit company to do that. It's okay with me. I haven't seen good product come out of any of the oceanographic research tool companies. So, how else can you do it? There are contract manufacturers. I work in Monterey, work right over the hill from Silicon Valley. When I was a defense contractor, we used contract manufacturers also. These are companies that aren't developing products. You come to them and say, here's a package of documentation, build me 10 of these. And you work with them to get them up and running, and they build 10 of those a year for you. Our pH sensor has always been built in our lab or at Seabird, and it's hand-built by very competent people. It's incredibly expensive, but when I started redesigning the pH sensor for higher reliability and more manufacturability, it was with the express intent in the back of my mind that we wouldn't be building them in our lab. So when we finally got prototypes working, I talked to Ken and said, Ken, get these built elsewhere. He goes, oh, no, this is too sophisticated to complex. And I said, well, done. So we found a contract manufacturer, Applied Engineering in San Jose, and we went and spent a fair amount of time developing what they call the process of record, which is the manufacturing assembly instructions. And so we did that, and now they're building 30 or 40 a year for us. It's worked out quite well, and they're doing it for less money than we can do. There are other options. We're going to have to speed up here. NSF has an ocean bottom seismograph instrument center. Make it possible to fund the construction of whatever, 20, 30 CPS, put them in a pool, make them available. This mitigates the problem of everyone having to absorb all the capital costs of CPF array. It's just like, ships and ROVs are actually equipped also, and it might be that one of the well-known philanthropic organizations would be interested in funding this, that there would be a pool or 20 CPFs, just like Schmidt Ocean Institute makes their boat and ROV available. So a whole bunch of other stuff. You could have sponsored builder workshops, DIY documentation. And if there was one group that was heavily into CPFs, they could provide CPFs also. And nothing prevents commercial companies to get involved in an open source agreement as long as it's a non-exclusive license. So they would be willing to say, yeah, we want to do it, and we're going to build them so well and so cheaply that people are going to come to us instead of building their own. Great. Okay, the other critical infrastructure is expertise. I'm going to sort of zoom ahead. Where's the expertise going to come from? You're not going to get me. Navarre's not going to provide you. NOAA's not going to provide you. So who's going to help people who aren't CPF knowledgeable or even profiling flow knowledgeable run their profiling flow program? Good news. There's a company right here in Seattle called Ocean Tech. Ocean Tech Connection. Avery Snyder, who was at UW, has started this company. He provides text. They do a tremendous amount of work with a range of profiling flows. They're very knowledgeable. This is, I'm pretty sure it's a for-profit company, and that's where the expertise lies. That's rentable. You can hire a tech to help run your CPF project right out of Avery Snyder's company. And I've talked to him, and he's very interested in this. So I'm going to zoom ahead. I got the hook from NOAA. Close. The data pipeline is critical. So right now, if I get my data in flow viz, it goes through the standard GoBGC processing and quality control process. Nobody at MRU, let alone the Argo data centers, has the bandwidth to handle that. Additional non-Argo data streams. So big question. The Argo BGC data process has excellent documentation. As far as I'm concerned, it's the best documentation I've ever seen with respect to processing and quality controlling oceanographic research data. Can that be open sourced? Maybe. I don't see any fundamental reasons why. It might take somebody or two people a year to make an open source product, but there's funding for that. And we want relevant data products. So we don't just want, most people can't deal with pH and salinity and up to oxygen and fluorescence. They need a product. If you're a fishery manager, you don't want those. You want products. And that's what things like NOAA Future C is doing. They're taking all that quality control research data, essential ocean variables, and turning them into products that fishery managers can say, okay, the take for next year's salmon season is going to be 10,000 pounds, whatever the number is. So those data products are important for non-expert research users. Lots of risks. Sensor maturity. Many of the GoBGC sensors are pretty mature. pH sensor is mature, but it requires expertise to use it. And that's not readily available. I have noticed there's a lot of talk going on about how to interpret FOBB and OCR data, and this is an active conversation. So it's just an open question. Do I have an answer? Nope. But it is one of the risks. I talked about the data centers. And the problem with the technical readiness levels, and I don't care if it's the NOAA TRLs, NASA has TRLs, the Department of Defense has TRLs, I don't care if any of it. They don't say who's demoing the system. So I can be TRL 7, and it absolutely requires me to demo the system. That doesn't seem really fair to me. You want to get to TRL 8, you need the non-developers to be demoing the system. So that's a self-inflicted requirement that I have. Targets, I've talked about many of the targets. I'm also interested in helping NGOs. So for example, the Alaska Marine Conservation Council is trying to manage their fishery. Let me use Sustained Lake Tanganyika as a different NGO. Small community-led organization in Africa trying to manage the Tanganyika ecosystem in order to improve the welfare of their local communities. Do they need a 50 CPF array in the Lake Tanganyika? No. They probably just need to make 1 or 2 measurements a year, 3 or 4 measurements a year, in order to understand what their baseline ecosystem looks like, how it's changing over the years. If they didn't have to buy CPFs, if they could go somewhere like the Marie's OTC company, and say, hey, come on out, we've got $10,000, make a measurement, come back in 6 months. That would be kind of awesome. Is this a realistic possibility? I'm going to go through, I'm not even going to go through this in great detail, I'm going to go really quickly. Yeah, I think it is. So the POSE solicitation is explicitly in phase 1 designed to figure out and to provide the training you need to evaluate the ability to build and operate on a open source ecosystem. And then the idea is to, is it feasible or not? That's the goal. Find out if it's feasible. As part of that, you develop a risk mitigation strategy for some of the risks I talked, all of the risks I talked about, and any more you can come up with. I think you'd also have to find funding to support a pilot project with existing CPF assets, like a marine CPR, MRV system, or a fishery management system, or whatever. And if all that's successful, you would apply for phase 2 funding, and then you'd execute phase 2 and the pilot project in simultaneously. So with that, bankability, we all know that this kind of stuff doesn't happen in isolation. It takes a village to build this stuff. Here's my village, and the work has been generously funded by the David Consumer Packard Foundation. And thank you very much for this. Questions?
I guess so. Okay.
Thanks, Gene. We'll start in the room. Well, and I'm gonna poke around and see if I can get questions from online if there are any.
So what is the major limiting factors for your lifespan up to 7 years?
I'm sorry, say again, please.
What is the major limiting factors for your lifespan up to 7 years, not longer?
So 7 years is Argo, Argo floats. They can go 7 years. It's the batteries, straight up battery.
Okay.
There are, of course, failures. Throw something over the side of the boat, things are going to happen. You won't get it back when they fail either immediately because of infant mortality on the sensors generally. But if you throw a working profiling float over the side, it'll last for 5 to 7 years. The thing will end in its batteries. By and large, reliability is a problem, but that isn't the primary problem.
So are you working, you mentioned Yichao, are you working with him for the thermal batteries?
I have done some work with Yichao. It's really great. He's got a fun project on it. He has a thermal capture system, but it needs a very specific temperature differential that may or may not be available in coastal zones.
Right.
Yes, please.
Yeah, so with a lot of the cost is in sensors.
More
You've
than
got-
2/3.
You have a unit here that probably costs similar to an Argo.
Yeah, they're very similar costs.
And so I guess the question is for only for 200 profiles, are you thinking what's economics? Is it that you recover these basically?
So absolutely.
Yeah.
So Argo floats, you off the side of a boat in the middle of the Pacific Atlantic, very rarely going to get, that is not the situation here. So for example, 200 profiles spread over a year. And winched, if you had a winched application, probably not as many, but not that much different. So the energy calculations are roughly the same. But rechargeable batteries, you go get it after 6 months to a year. If it's anchored, it's easy to go get it. I know where it is. Even if it's floating, not that far offshore, you go get it. Go out there with another one fully charged, you keep it over the side, grab the one that's expended, and come back and recharge it. That's absolutely the plan, yes.
And I was going to say, just for people online, if you could enter it either in the questions or the chat. It's rather hard for me to see the questions, but we have one here that we'll go to quick before the room. This is, sorry if I missed this, but any thoughts on dealing with biofouling effects for an extended deployment?
I'm very much hoping somebody else solves that problem. I'm sorry, I just don't have an answer. I will tell you that we have deployed these things for weeks at a time in less than 90 meters of water, generally parking on the bottom, and surprisingly little biofouling. I don't believe that's going to be the case. I've spent too much time scraping barnacles off of stuff to believe that that's, I think we got lucky. For most of our applications, I can see our long-range AUV coming back after several weeks at a time, and it has spot accumulation. Good news is, most of the sensors are pretty biofouling compliant. They can deal with some amount of biofouling. And the CPF has enough buoyancy to keep going up and down, even if we have a pound of muscles attached to it. And the other thing is, so the advantage of either the winched or non-winched approach is we keep track of exactly how much buoyancy it takes to get off the surface. If that number starts to accumulate, I'm sorry, let's say it differently, how much buoyancy it takes to get off the bottom. If that number starts to increase, then we call the mission and go in. Yes, please.
So I realize that your interest and also Ken's interest is in profiling. But does Embari have a group that is working with uncrewed surface vehicles at all?
It's a very small effort in uncrewed surface vessels. We do have several wayfinders that we run regularly. We did develop them, many things we buy and modify from Liquid Robotics. Sail drones, super exciting project, doing much in that world. I do think that the ESP, the environmental sample processor that we also built in our morning, went out on a sail drone once. And I think they have nice, but that's not our expertise.
Okay.
Sorry. You have a project? Yes, please.
do you have a way to detect the bottom so that it won't run into mud?
So there is an algorithm and you're going down, right? The question is, have you hit the bottom? It's actually kind of hard to decide because we're not going very fast. So if we stop descent, we have a fairly accurate pressure as to certain, it's the Super 41 CGD. We stop going down for a certain amount of time, then we call it anchor. Now, you can't differentiate between running into a kelp wall and hitting the bottom. It's the same physics as far as the profile of the float is concerned. But in either case, we call it anchored. And then we have various algorithms that say, okay, am I still anchored? Have I leaped up? Do I need to re-anchor? This is what a vast majority of the software is. It's like dealing with outside the box cases. It's easy to detect the bottom the first time. Then what happens? Like that. So yes, we do. There's just not much to be done. So for example, we don't have an altimeter. We're trying to minimize the power consumption. You really want to stay a certain distance off the bottom, put an altimeter on this thing, and that's what we closed our control loop on. And the good news is that just design a fair amount of equipment to interface with a fair amount of instrumentation, and I've gone to great lengths to make it fairly easy to interface almost any serial instrument to this gizmo, as long as it's not a wacky protocol. If it is a wacky protocol, nothing's wackier than a Seabird 41 to deal with. But yeah, so we can add instruments fairly easily, and we have.
Have you figured out a way to quality control the pH nitrate data of deep oxygen?
That's a fairly heavy duty science question. So I will tell you what I understand to be the case. So Josh and Tanya, of course. And look at that, you drove all my customers away, like, hardcore science questions. So the Hebrew, they run the wire model and another model, and they keep looking at deep pH. I don't think they look at deep oxygen. I don't know.
For all the BGC Argo, and I think for UE spray gliders, they use deep oxygen with the algorithms to get pH and nitrate exact. And UE is able to do it, because he can do it at least at 500 liters with sprays. But with this, I don't know how that would work.
So you certainly know more about this than I do. I listen to these conversations, and I'm kind of astounded at how much energy goes into quality controlling pH data. I didn't actually know nitrate was that big a problem also.
Yeah.
Yeah,
Different issues.
I'm heavily involved in the pH work, so I listen to these conversations, and I just go, if I ask, how is anybody other than our group or very few experts in the world going to take pH data and do anything useful with it? I don't know. It's beyond it's not my area of expertise. But if you look at, for those who don't know, if you look at Tanya and Josh's Argo process for QCing pH data, it's a nice document. It's not, correct me if I'm wrong, please. It's not like, here's all the answers, just do this and you will have pH to 10 millipH. It's not that, but it's, here's what the state of the art is, do this. And you will have a pH measurement with some uncertainty in it, but this is the state of the art. It's duplicatable by other people. At least I can read the document and say, yeah, I can write an algorithm to do that if I had to. But it's an ongoing, cutting edge process.
Hi, I'm a mechanical engineer, so I'm more interested in the winch design, a little bit more of that. So I assume the concept is that you keep the float buoyant and then winch it up and down. And I know it's just a concept and there hasn't been any testing done. But do you have ideas about how to prevent any twisting in the line as it's moving up and down, assuming that this float could spin when it hits certain currents?
Yeah. So great questions. Spinning isn't a problem. You can deal with that with swivels, right? By using Spectrum Line, which is a torque balanced cable. Spinning isn't a problem. Keeping the line on a winch from snarling, if you've ever seen a fishing reel, they snarl on a regular basis. You need a level line. There are some other ways to do it without level lines. We can talk in detail later. I'd be happy to. But yeah, so I built autonomous winches that work on surface buoys. Never one that was in the water. But there's a bunch of challenges. And it's kind of the same thing as my open source question. Do I know I can build a winch that will work for 200 profiles spread over a year? Do I think there's a better than 50-50 chance I can? Yeah. And what happens if it does snarl? Well, there'll be a cutter built in that just cuts the thing loose and you go get it. So it's not the worst case. And you can cruise with the winch isn't that complex to design. It's really, I always say that, take my time estimate, multiply by 2. It's still not that much time. And so you can build one, test one, and have a pretty good idea of how reliable it is. I don't think there's a way to analyze your way to a reliability number for an underwater winch. I think you have to build one.
I have one last question. Oh, yeah. And that is, so if someone's interested in this, how do they go about getting one? And what do you think the timeline is for actually using this as a product outside of the MBARI?
So it all depends on what MBARI wants to do. My guess as to the future for the CPF project is we're going to finish the engineering development this year. And our lab is heavily, fully on board with GoBGC. The project's being run in our lab. And we're fully booked. I don't think we're going to do a lot more engineering development on the CPF. I would love to, but I don't think MBARI has to make choices. And our lab's goal is GoBGC and follow on. And we hope very much there's going to be follow on. We've got indications to that end. But MBARI also wants to move our technology out. So 3 CPFs. Somebody wants to talk to MBARI about using them for a pilot project or getting their hands on the drawings and the software. I'm happy to talk to you about that and see if we can make that happen. So I'm wide open to anything from providing drawings, documentation, and occasional consultant support to things that are much more concrete and can help move the technology out of MBARI into other places where it can be used effectively. MBARI would love to see that happen. So I'm open. Please tell your friends. Bring applications.
Excellent. All right. Well, with that, I think we'll close this off. Thank you, Gene.
Thank you. I appreciate the opportunity.